Hi everyone, I'm Wenxue from HKUST. Today I'm very happy to present our work, FLB, fine-grained load balancing for lossless data center networks. And this is a joint work with my colleagues, Jinbin, Xiangzhou, Junfeng, Bowen, my advisor, Chen, and other collaborators. We all know that RDMA, especially RDMA over Converged Ethernet, RoCE, is widely deployed, and many companies have reported their experience of deploying RDMA in large-scale data center networks. For example, Microsoft Azure, Alibaba Cloud, and Google Cloud. And currently, RoCE relies on priority flow control (PFC) to transfer the Ethernet fabric into a lossless fabric. PFC is a hop-by-hop mechanism. When the downstream queue length exceeds a given threshold, let's call it X off, this downstream port will generate a pause frame to the upstream port. And after receiving this frame, this upstream port will stop its transmission. And when the downstream queue length decreases below a given threshold, for example, X on, it will generate a resume frame to the upstream port. And after receiving it, the upstream port will restart the traffic transmission. At the same time, we know that modern data centers usually provide multiple parallel paths. For example, the NVIDIA SuperPort provides rich parallel paths for any GPU to GPU pairs. And because of this, load balancing is very important. Load balancing is also known as multi-path transmission. We must utilize this parallel path to do some useful stuff. For example, avoid congestion and hotspot, and handle failure or something else. In this project, we first investigate how existing LB schemes perform in lossless RDMA networks, and we find that they are inefficient. The first reason is that their inflexible rerouting leads to load imbalance and link under utilization. We use a small-scale testbed to investigate their performance. In this experiment, there are 3 long-running flows, flow 0, flow 1, and flow 2, and several burst flows starting from 4 milliseconds. And we use DPTK and P4 switch to implement the baselines. We first look at how ECMP performs. We run the experiment multiple times, and we find that in some round, flow 1 and flow 2 are hashed to the same path, path 2, by coincidence, and this causes congestion. And after the congestion, ECMP cannot reroute flow 1 or flow 2, even though there's a path 1 which is available and underutilized. So we measure the throughput of all long-running flows as shown here. Both flow 1 and flow 2 experience throughput degradation. After this burst flow, call this PFC pause at about 4 milliseconds. Both of them, flow 1 and flow 2, are affected. So we conclude that ECMP is inflexible. Now we look at let flow. Let flow is a representative flow-lit-based LB mechanism. Also, we run the experiment multiple times because the entire flow 1 or flow 2 is treated as one flow-lit. So in some round, let flow maps both of them to path 2 by coincidence, therefore causes congestion. And After congestion happens, that flow fails to reroute flow 1 because flow 1 is an RDMA traffic and it lacks flow rate interval. As a result, both flow 1 and flow 2 experiences throughput degradation and PSC pose influence. So we also conclude that that flow with a fixed flow rate interval is inflexible. The second reason is that multipath transmission expands the influence scope of PSC's head-on line blocking. I'll show an extreme case here. We construct an experiment where host 0 to host 30 simultaneously transmit traffic to host 31, creating a long-living 31 to 1 incast pattern. We measure the number of paths that receive the pulse frame during this experiment. We compare several mechanisms, ECMP, packet spray, and packet spray plus DCQSN. We find that ECMP only causes about 30 paths being pulsed, while packet spray results in all paths, about 340 paths being pulsed. This is because under packet spray, the data is spread across all paths. We also show that CC, specifically DCQSN, is not very helpful because it cannot to quickly eliminate congestion and stop the PRC pulsing. So in this project, we ask a question, can we design a load balancing scheme for PRC-enabled lossless RDMA data centers that achieves high link utilization and eliminating PRC side effects? This goal has 3 sub-goals. The first goal is that we must flexibly reroute the traffic to effectively balance load and enhance link utilization. The second goal is that we must eliminate the head-on line blocking and congestion spreading during PRC triggering. And the third goal is that to reduce dependency on complex congestion control schemes. We answer this question using FLB, fine-grained load balancing. The key idea of FLB is that we observe that in the ideal situation, when there is no congestion, all packets should be transmitted via multiple paths. When congestion happens, the packets of congestive flow should be transmitted using single paths to avoid congestion spreading. So based on this observation, we obtain the following principle that the uncongested flow should be transmitted by multipaths, and the congestive flow should be transmitted via single paths. Based on this key idea, FLB is composed of 2 modules. The first one is the routing and the rerouting module, which is responsible for the multipath selection for uncongested flow. So if an arriving flow is not a congested flow, it will be handled by the routing and rerouting module. In this module, FLB try to reroute flow without a fixed threshold, and during this process, it avoids packet reordering. If there is a congestion, the destination switch will generate notification to the source TOR switch. This switch will record the congestive flow in the flow table. So if the arriving flow is a congestive flow, it will be handled by the isolation module, where FLB separates rather than spreads the congestive flow into one or several isolation paths. Now I'll go deep into the routing and rerouting module. If arriving uncongested flow is a new flow, very simple. This module will select a path with the minimum delay for it. And if this flow is not a new flow, means that it already has a path called current path. And this module will try to find a faster new path for this flow. So if a faster path exists and the delay difference of this new and current path is less than the time interval of current and the previous packets, this module will assign this path for it. This complex condition is to avoid packet reordering because faster path cannot be too fast. If it's too fast, it will cause packet reordering. Because we have to measure the path delay, so we actually require coordinations between destination and source TOR switch. One specific challenge is that how to measure one-way delay when the switch clock is not synchronized. We address this challenge by actually using the one-way queue delay. There are 4 steps to measure the one-way queue delay. First, the source switch will add the departure time step T1 in the packet header. And when receiving it, the receiver switch calculates the one-way delay by subtracting the T1 from the arrival time T2. And this delay is sent back to the source TOR switch. And the 4th step, the source TOR switch will calculate the real one-way queue delay by using the notified one-way delay minus the base delay. So by using this equation, if there is a clock error between the source and dest TOR switch, there is an error in this one-way delay and also an error in this base delay, and the error minus error, so the error is cancelled. So the one-way queue delay is accurate. And the base delay is the one-way delay without any queuing delay. It can be actually obtained using the minimum history one-way delay. Now I'll go deep into the isolation module. When the congestion happens and the queue length of one egress port reaches the isolation threshold, we configure this threshold to less than the PFC threshold. So FLB acts before PFC is triggered. And then a congestion notification frame containing the flow ID of congested flow is sent to the source TOR switch. And after receiving it, the source TOR switch stores this FID, flow ID, into a flow table. The switch will isolate the subsequent congested flow onto a set of isolation paths. The switch will also have to maintain to track the isolation paths. I'll quickly go through the implementation and evaluation. We implement FLB using the Tofino-1 programmer switch. We measure the resource consumption, and FLB only adds minimal overhead compared to ECMP and let flow. We use this testbed to evaluate the performance of FLB. We use 20 servers, each with Connect X5 NIC and DBTK software. We enable the host 0 to host 16, generate dynamic traffic according to the web search workload, and we let host 3 to host 16 start sending traffic simultaneously, so they are burst flows. I'll show 2 representative results here. In this paper, we show we measure path level metrics and flow level metrics. For the path level metrics, we compare FLB to ECMP, let flow, MP RDMA, and Learn plus DCQSM. we measure the average link utilization. The results show that FLB achieves higher link utilization on different paths than the other schemes. For the flow level metrics, we measure the flow completion time, FCT. FLB achieves the lowest average and 99 percentile FCT of all flows. Specifically, FLB can reduce the average FCT by up to 48% compared to existing baselines. Okay, that's all today. Thank you for listening. If you are interested, you can contact Jinbin and me using these two emails. Now I'm glad to take any questions.